Hello, everyone. I am trying to recreate the lecture that we had on April 21st. Turned out that I had some technical issues and I stopped the recording in the middle and I did not complete it. So I'm just trying to record it just for your record so that you can refer back to this material. And to do that first, and the goal of this lecture is to figure out how certain assumptions that we make about car following, like how a follower's behavior changes depending upon their own speed or how far they are from the leader in traffic. How does that change their acceleration behavior? Assumptions about those deceleration or acceleration behavior ultimately impact the macro level assumptions that you might be making about speed density relationships. And you can actually integrate these car following behavior over time to obtain those macro level relationships. Before we get started on that, I want to quickly go over some integration, some indefinite integration that we'll need a refresher on. So let me go ahead and share my screen. Okay, so there is this idea about how do we integrate things. So as you probably know, integration is basically the process that's opposite of differentiation. So when you're trying to find any kind of integral, like for example, here I'm trying to find what is the indefinite integral for 1 over t squared dt, or if I'm trying to find the integral of 1 over t dt, or I'm trying to, in general, find what's the integration of t raised to power n dt. Basically, our goal is to find the function which, when you differentiate it, you get what's inside your integrals. So for example, if I'm trying to integrate 1 over t squared or t raised to power n dt, the integration is defined as 1 over n plus 1 t raised to power n plus 1. And n could be any number other than -1. It doesn't have to be integer. It could be 1.5, it could be 2, it could be 2.5, it could be any number other than -1. And if you were to integrate, and if you were to actually differentiate this piece back, okay, this piece back on the right-hand side of this equality, you will get back t raised to power n. Okay, if you differentiate this with respect to t, you will get exactly t raised to power n. And that's the idea of integration. And then I have a c at the end, which is a constant number independent of t, because, and we always add that because we know when we differentiate the number c, the constant number c, with regards to a t, you will get 0. So that's why we always add a plus c to the indefinite integrals. And as I said, n cannot be -1. So what happens when n is -1? We know that, so then that becomes 1 over t dt. And the integral of that is natural log of t plus c. And again, c being that constant that we use all the time, because the differentiation of that number with respect to t would be 0. Okay? And we can quickly do 1 over t squared dt. It'll be n here is -2, t equal to, n equal to -2. So 1 over -2 plus 1, t raised to power -2 plus 1. So the answer then would be -1 over t plus c. Okay, and then you could solve. I asked you in the class to solve what happens when n equal to -3. It becomes 1 over t cubed dt, and then you just plug in n t equal to -3 plus 1 t raised to power -3 plus 1 plus c. You get -half t raised to power -2. Okay. Now, one more piece of integration that would be useful to us for in this class is integration by substitution. Integration by substitution is useful to have some complex problems, to solve some complex integration problems that where we don't know the exact formula of integration. For example, for t raised to power n dt, I provided you with the exact formula on how to integrate right here. Okay. I gave you the formula. Now, if you look at this little integral here, t divided by square root of t squared plus 1 dt, there is no formula for that. It doesn't take the form t raised to power n dt. This problem here is much more complex. And because this problem is much more complex, we need to figure out what should be the method that we should use. So in this case, the method we use is the method of substitution. For substitution, what we do is whatever is in the denominator or inside a complex operation like a square root, we typically assume that to be another variable, u. Okay, let's call that u here. And why do we do that? Because typically when we do that function, we assume that to be something else, the differentiation, typically you're able to replace what's in the numerator with something else as well. So for example, in this case, if I assume t squared plus 1 to be u, I can find out if I differentiate both sides with respect to t, I'll get 2t on the left-hand side and du over dt on the right-hand side. And that tells me that I can replace, anytime I see t dt, I can replace with half du. Okay, and half is a constant number, so it can stay inside the integral. So anytime I see that, I can replace t dt with half du. And that's exactly what I have in the numerator, t dt to be half du. Okay, so it becomes, and this is not complete, so I should probably complete it. So this becomes 1 over 2 So this becomes half outside the integral from half du, and t dt becomes half du, and half can come out of the integral because it's constant. And this becomes, because I've substituted inside the square root to be u, this becomes u raised to power half. Now, if you see this problem, this is basically a problem just like this. It's essentially a problem that looks just like this. Du raised to power u raised to power half. It is a problem like this now, where n is equal to negative half. Okay, and you can solve this problem. Now, if this was a class, or a mathematics class on integral calculus, you would have to know quite a bit and learn quite a bit and spot these, what should be your substitution. That'll take some practice and some doing. And because my goal in this class is not to teach you integration, I will just stop here and I'll just ask you to kind of keep an eye out on what's in the denominator, treat that as a substitution variable, u or x or whatever you want to call it. And then your denominator or numerator will become the derivative of the new variable that you've created. Okay, and then you will be able to solve the problem. Okay, so this was my brief overview of integration. If you have still want to clarify it more, if you're more interested, if you go on YouTube and search for integration by substitution, you will be able to find a lot of material on that. Okay, so now I'm going to switch gears and talk about the actual material that we're going to go over. Okay, welcome back. I am talking about the sheet that we annotated in the class, and I want to zoom in on this print in this PDF sheet a little bit further so you all can see it. And what we are trying to do here is we are taking and we are thinking about the microscopic behavior of individual vehicles as they follow the leader in traffic. And this is called the car following theory, or the follow the leader theory. It considers spacing and speeds of individual vehicles. So if you consider two individual vehicles, A and B, they're shown in this figure here. Car A is the leader, car B is the follower. And let's say from some reference point, the coordinate of the front bumper of car A is xn. Coordinate of the following car is xn plus 1. And we always define the subscript of the leader to be a smaller number. So you could define it as xn minus 1 for the leader or xn for the follower. But we are not doing that. We are doing xn for the leader and xn plus 1 for the follower. So follower will have always a larger subscript because they follow the leader. So n comes before n plus 1. So leader comes before the follower. And we are defining a safe distance S that the follower would want to maintain if both cars were at complete stop. Okay. So this is your S value. And then what would be the spacing that the follower would want to maintain while moving? That would be defined as P. And that's the parameter rho times x raised to power, or x dot n plus 1. And remember, n plus 1 is just a subscript to define the follower B. And x dot, remember, dot stands for derivative with respect to time. So if this dot, if you look at this dot here, if you look at this dot right here, this dot stands for derivative with respect to time, and xn plus 1 we know is the position of the follower. So when you differentiate that with respect to time, you get the speed of the follower. So what we are suggesting here is that the spacing that the follower wants to maintain will be some parameter rho times the speed of the follower. When this speed is 0, basically when they are at complete stop, they will try to maintain the distance S between the leader and the follower. So if you go back up now, if the driver of vehicle B maintains an additional separation distance P above the separation distance at rest S, such that P is proportional to the speed of the vehicle B, you will see capital P is equal to rho times speed of the n plus 1 vehicle. Okay, n plus 1th vehicle or the following vehicle. So if you want to write that as a position difference, the position differential between xn and x minus 1, or xn minus xn plus 1, the position difference in this case then would become S plus, it'll become S plus rho times x plus 1 dot, S plus rho times x plus 1 dot. Okay. Now, if you differentiate this expression with respect to time and rearrange it, you get equation 628, which is, so if I differentiate this side, I'll get xn with respect to time, I get xn dot minus xn plus 1 dot. So now this has become the speed differential. This variable goes to 0. And then this becomes 1 over rho, and then xn plus 1 dot differential becomes xn plus 1 double dot. The 2 dots means you take the derivative of xn plus 1 2 times with respect to time. And as if you recall from your physics, when you take the derivative of the positioning 2 times, you get acceleration or deceleration, whatever. It's a rate of change of speed. So first dot gives you the rate of change of location, which becomes speed. But if you take 2 dots, you get the rate of change of speed, which becomes acceleration. This equation is the basic equation of microscopic models and is describe the stimulus response of the models. Okay, so basically what this is telling you that this speed differential right here is your stimulus, and the acceleration or the deceleration of the follower is the response that the follower gives. And you could see that we are saying that if the speed differential is higher, if the speed differential is positive, if this number is positive, okay, xn is higher, xn dot is higher, okay, if the leader is going at faster speed, the follower might want to accelerate because the xn plus 1 double dot would be positive in this case, because this expression would be positive. And at the same time, if this expression is negative, that means the follower has higher speed. That means this expression will be negative. And at that level, at that point, the follower might have to decelerate so that they don't bump into the leading car. Now, 1 over rho we can define that as what we call lambda. And then we also can introduce one more thing here, is what we call the reaction time. Researchers have shown that a time lag exists between a driver's response to any stimulus that is induced by the vehicle just ahead of 6:28. And so that's why we are saying in that stimulus response, we're going to say that this equation 6:28 will not take place at exactly the same time. So it's going to happen after a lag of time, capital T, which is what we call the reaction time, capital T. And what we can essentially say here is xn plus 1 double dot T plus capital T. So you're, as a follower, your acceleration or deceleration at time T plus capital T would be dependent upon what was the speed differential at time T. So you'll notice this speed differential at time small t, and you will react and you'll attain a deceleration or acceleration at time T plus capital T. Capital T is a constant, which is what we call the reaction time. That time lag is called the reaction time. And one thing I also want to say here, and based on the question that I got asked, this quantity in parentheses, this T plus capital T is not being multiplied by xn plus 1 double dot. It's basically denoting the time at which this deceleration is defined for. Time for which this deceleration or acceleration is defined for. Okay, so it's not a multiplication. Same thing, same idea applies to this T and this T. These are not being multiplied to these quantities xn plus 1 dot. They are basically denoting that these values, these speed values, are being observed at time T. Okay, we didn't do that here. But this is just to differentiate, because both sides of this equation were being observed at the same time. But now that we want to denote the significance of the reaction time, we want to make sure that we denote that time T. So again, this is not a multiplication. This is just to denote that you're observing the speed values at time T and these acceleration value at time small t plus capital T. Okay, so I want to clear all drawings here now. So I did a couple of things to the equation. I've defined that at two different time frames, and then I'm calling 1 over rho to be my lambda, and I'm going to define that lambda as my sensitivity parameter. So what might be the follower's acceleration or deceleration be sensitive about? Okay, so that's what we're going to think about next. So as we go down to the next page, T is the time lag of response to stimulus. And lambda is 1 over rho. It's also called the sensitivity. So now we are defining a general expression for what we call the sensitivity parameter. So a reasonable way to think about lambda is that lambda is a constant times the speed that the follower has, the xn plus 1 raised to power m t plus t. So again, t plus t is not being multiplied to this value. It's just defining the speed at this time, t plus capital T. Okay, and I'm saying that the sensitivity parameter could be defined as x dot n plus 1 t raised to power t, speed of the follower, raised to power some constant value, capital M or small m, divided by the spacing between the leader and the follower at time t raised to power L. These m value and L values, these m and L, they are constant values. The numerator as a whole is the speed of the follower at that time when they're accelerating or decelerating. And this denominator defines the space headway. This denominator defines the space headway, which is basically the same as spacing between the leader and the follower. So space headway will probably be the correct parameter. So let me actually draw it out. So I'm going to call it not spacing, but I'm going to call it space headway. So what we are saying here is that if your space headway is large, you're not going to be as sensitive to what the leader is doing. So that's why it's in the denominator. And by raising it to power L, you're basically more sensitive or less sensitive to that spacing. And then if your speed is high, this value, what is the numerator defining? If your speed is high, if this speed is high, then you're going to be more sensitive because you might be catching up to the leader quite a bit sooner if you're traveling at a higher speed. Now, so if you want to just go back to that equation 629, you can now write the whole expression. So basically, this is combining this expression for lambda and the previous expression that we had, and this expression for xn plus 1. So these two things now are being combined. This expression and this expression are now being combined. So this expression for xn plus 1 double dot and this expression for lambda are now being combined into this one big expression which gives you the acceleration at time t plus capital T, some constant a, xn plus 1 raised to power m, t plus capital T. And again, a more correct way of saying that would be to take this whole thing and raise it to power m, because t plus capital T is not being multiplied. It's just defining that time at which you're observing that speed, raised to power small m, divided by the spacing and times the speed differential between the two, where a, l, and m are three different constants. So now you've combined equation 629 and 630 into equation 631. This microscopic model, equation 631, can be used to determine the velocity, flow, and density of a traffic stream. And this is where what you learned in CE 321, your introduction to transportation engineering class, where we learn about the Greenshields model or the Greenberg's model and things like that, how you can now, I'm going to try to show you how this type of things could be used to derive those macro level relationships between speed and density. Okay, so let's think about this. I'm going to try to draw just to kind of define for the equation for you. So if you remember the Greenshields model, what was the Greenshields model? If you define speed and density on x and y axes, okay, and let's say if you have, this is your density axis on the x-axis, and this is your speed axis on the y, you can define speed density as a linear function where the speed goes down as density increases. So as you increase the density, the speed goes down in a simple linear fashion. You can actually derive this, and this is what we used to call in CE 321, this is what we used to call the Greenshields model. Okay. And you can derive that Greenshields model by making certain assumptions about M and L. And in this class, just to keep the math simple, we are always going to assume M to be a 0 value, because if you put in M equal to 0, this part of the numerator goes to just anything raised to power 0 is 1. So this whole thing becomes 1. And in this equation, and your textbook basically assumes M equal to 0 and L equal to 1. Okay, this Garber and Hoyle textbook that I'm using here assumes M equal to 0 and L equal to 1. By the way, for Greenshields model, what you will do is M equal to 0 and L equal to 2. And that is what I'm asking you to do for your homework problem. So you will demonstrate that for your homework problem, where I'm going to assume M equal to 0 and L equal to 2. But in this textbook here, we are going to work on M being equal to 0 and L being equal to 1. Okay. If M equal to 0 and L equal to 1, you'll get xn plus 1 dot t plus t. So same thing as the left-hand side, nothing changes there. But if you substitute m equal to 1, this piece here, this piece of the equation right here goes to 1, and then this becomes the whole numerator, xn dot t minus xn plus 1 dot t becomes the speed difference divided by, and you assume L to be equal to 1, so xnt minus xn plus 1t becomes just that, because you've assumed L to be equal to 1. So you just get like, this becomes raised to power 1, right? So this becomes raised to power 1, which is nothing but, you might as well not have it here. Now, if you assume this denominator, so now this is this time where we're going to exercise that integration by substitution approach, okay? So this is what I'm trying to tell you. Like, if you assume a steady state and you can integrate this expression with respect to time, okay, you can find the average speed of the followers. Okay, you can find the average speed of the followers. So if you integrate this with respect to time, your left-hand side simply becomes, if you integrate acceleration with respect to time, you simply get the speed on the left-hand side. The right-hand side is a little bit more complicated, and that's where you have to apply the integration by substitution approach. So I'm going to assume this to be, and in the class I assume this to be u, but let me make it into a v here. So let me come down a little bit and clear this out. Okay. So in the class, I asked you to do a substitution integration by substitution by substituting this to be a u value, but it looks like this textbook by Garber and Hoyle uses u for the speed later on. So I think a good approach might be to call this v instead of u. Okay, so I'm going to just call it v now instead of a u. So let's substitute this denominator expression, this part of the expression, to be a v. So v becomes xn minus xn plus 1. Okay, and I'm not putting t because they're all at the same time t. So then dv over dt, okay, dv over dt becomes, because I'm differentiating both sides by with respect to t, xn dot minus xn plus 1 dot. So then dv, I can write anytime I see a dv, or anytime I want to substitute xn dot minus xn plus 1 dot dt, which is the numerator of my integration on the right-hand side. When I'm trying to integrate this expression with respect to time, when I'm trying to integrate this expression with respect to time, this is what's going to be my numerator. So I can substitute that denominator with dv. So I'm going to get, instead of when I'm trying to integrate, instead of this whole expression, instead of this whole expression now, instead of this whole thing, instead of this thing, I'm going to get, on the right-hand side only, I'm going to get a times dv over v, okay? And I'm going to try to integrate this expression with respect to v. Now, dv over v, it's v is equal to -1, so that's where I have to get ln v. So if I integrate that, I'm going to get, if I integrate it, I'm going to get a times ln v plus a constant, okay? And this is exactly what we have, because if you recall, this is what I had assumed the value v to be. V was xn minus xn plus 1 dot was my v. So ln equal to ln v, a times ln v plus c. And this is exactly what I have right here. Okay. And because I have that, because I have that, I can write this as xn plus 1. I can see this has become speed equal to, so this xn plus in a steady state, because if you're able to maintain an average speed and you're looking at all followers together, you can call this the speed of the traffic, average speed of the traffic stream, u. And on the right-hand side, you get a times ln xn minus xn plus 1 plus a constant. Now, remember, this is something that we did not get a chance to go over a whole lot. And in the class, towards the end, so this is something that you should pay attention to, xn minus xn plus 1 dot equals to average space headway, which is essentially nothing but a reciprocal of the density. So K, I'm representing K as my density of traffic stream. And we know that density is opposite of or reciprocal of the spacing. So that's why I'm able to replace that. So I can get U equal to A times ln 1 over K plus C. Okay. Now, we still want to figure out this capital C, and this is what we usually do it using what we call the boundary condition. And the boundary condition for us would be, when does the speed of the traffic stream become 0? And we define that condition where K becomes equal to jam density. So if I define Kj as my jam density, at which the speed is basically 0, okay? So I can use that if U equal to 0 at K equal to Kj, where K is my density and Kj is jam density, I can figure out the value of C when I plug in U equal to 0 equal to A times ln 1 over Kj. So if you substitute K for Kj right here, your speed should be 0. And then you can define the C value as C equal to negative A ln 1 over Kj. And your equation then becomes, if you were to substitute for C in the equation for U, your equation then becomes U equal to A times ln 1 over K minus, and this you're substituting for C now, minus A times ln 1 over Kj. And then you can sort of, because natural log difference becomes the ratio and Kj is the negative part, you will be able to develop A times ln Kj over K, okay? Kj over K as your answer. So this is what we call the Greenberg's model. And Greenberg's model, if you draw it out, it looks a little bit different than the Green-Shields model. So if I were to draw it out, let me draw out some straight lines. So this is what it would look like if you actually plot the speed differential curve for this. And then again, same thing here. You have the density on the x-axis, and then you have the speed on the y-axis. This is what the curve would look like. And it's going to be asymptotic and it'll approach, essentially what will happen is that it's going to approach the x-axis and y-axis, okay? But it will not touch that. This is basically a logarithmic expression. So this is what the speed density looks like. And then people have found that, on some ranges of speed and density, Greenberg's model is more appropriate than Green-Shields model. So this is what the plot would look like from Greenberg's model. Okay. So I know there was a lot of complicated math here, but all of this is to say that if you make certain assumptions about your microscopic car following approaches, you actually get some steady state macro level relationships that we have already learned about. So those things are not inconsistent with each other. In fact, they're very consistent with each other, as they should be, because in steady state flow, you should have your micro level car following behavior be able to describe your macro level traffic flow relationships. And this is what I was talking about earlier. This is my Greenberg's model, but if M is allowed to be 0 and L is equal to 2, we obtain the Green-Shields model, which happens to be your homework problem that I've assigned to you for due for next week. With that, I'm going to stop this discussion. And if you have any questions, please feel free to reach out during office hours. I would look forward to speaking with you. And there would be a problem like this in the test. I would always still have M equal to 0, but I will ask you for different value of L. And remember, L doesn't have to be an integer. It could be 1.5, 2.5, whatever. And you should be able to sort of replicate this process for any value of L and be able to integrate those things as in terms of a speed density relationship. Okay, thank you very much.